Welcome to the lecture series on process integration. This is module 4, lecture 8, area targeting part 2. In this area targeting, we will see that how to do the area targeting of heat exchanger networks when the heat transfer coefficient of all streams are equal. Heat exchanger area target is an important target, as by knowing the area of a heat exchanger network, we can estimate the capital cost of the heat exchanger network very accurately, and this helps us to optimize the network or to select a optimum network out of many alternative combinations of heat exchanger networks. The principles of minimum area of a heat exchanger network is detailed in next slide. Now, to calculate the area of a heat exchanger network, which includes the area of heat exchangers which take part in process to process heat transfer, as well as the area of the heaters and area of the coolers. For this purpose, a BSCC and BCCC has to be plotted. That means, balanced hot composite curve and balanced cold composite curve has to be plotted. The figure shows such curves. Now, in this figure, if it is broken into several components, that means several intervals, then we can have an interval like this, which is called interval I. If we see this interval, the hot stream goes from here to here, that means the temperature drop takes place in this direction, and the cold streams temperature rises in this direction. If we see these two lines, then it resembles with the temperature profile of a counter current heat exchanger. And to calculate the area of a counter current heat exchanger, we should know the value of Q, that is capacity of the heat exchanger, which can be given by the distance from here to here, because this is the delta H axis and this is the temperature axis. So, Q is known. The log mean temperature difference can be calculated from temperatures of these two end, that is, this is hot in, this is cold out, this is hot out and cold in. Using these 4 temperatures, the log mean temperature difference can be found out. If the overall heat transfer coefficient or the individual heat transfer coefficient of the streams which are present here and the streams which are present here are known, then we can easily compute the area of this segment, that is interval I, of the balanced hot and cold composite curve. So, the balanced hot and cold composite curve gives me a way to find out, or a method to find out the area of the heat exchanger network. We can divide the balanced heat composite curves in different intervals. We can find out the area of each interval, and we can add them up to find out the total area of heat exchanger network. Now, in this we consider that the vertical heat transfer takes place. That means, vertically the heat moves to the cold streams, and this is possible if I split the hot streams of interval I and I split the cold stream of interval I in such a way that the number of splitted hot streams and number of splitted cold streams becomes equal. So, that every splitted stream gets an opportunity to transfer heat to the corresponding splitted cold streams. Now, how this will be done? Now, let us concentrate on this part of the splitting process, where we are matching 2 hot streams with 3 cold streams. That means, in interval I, in the composite hot stream there are 2 hot streams, and here in the composite cold streams there are 3 cold streams present. Now, as there are number of cold streams equal to 3, then each hot stream will be splitted into 3 parts. So, the stream number 1 is splitted into this part 1, 2 and 3. Number 2 hot stream is also splitted into 3 parts 1, 2 and 3, and the cold streams are splitted into 2 parts, which is the number of hot streams. As number of hot stream is 2, each cold stream will be splitted into 2 parts. The third number of cold stream is splitted into 1 and 2, fourth number 1 and 2, fifth number 1 and 2. If you split in this way, the number of hot streams, that is splitted hot streams, is 6 now, and the number of splitted cold stream is 6 again. So, the splitted part of the hot stream 1 can exchange it with the splitted part of the hot stream 3, and in this exchange the area is 1,3, the Q transacted is 1,3, U is 1,3 and delta T ln is 1,3. Similarly, when the third splitted part of the hot stream 2 is exchanging heat with the splitted part of the cold stream 5, the area is 2, 5, 2 stands for this and 5 stands for this. Q is 2, 5, U 2, 5 and delta T ln 2, 5. When we break these streams in such a way, one can guarantee that vertical heat transfer will take place within the enthalpy interval. This type of splitting arrangement is assumed for all enthalpy intervals. Now, the computation of area for a single countercurrent heat exchanger requires the knowledge of in and out temperature of the streams to compute log mean temperature difference, overall heat transfer coefficient U and the total heat transfer Q. And if it is so, then we give the area with this equation, area is equal to Q divided by in brackets U delta T Lm, log mean temperature difference. The area is computed assuming overall countercurrent heat exchange, which manifests itself as vertical heat transfer. Now, the minimum total area could be taken as the sum of the areas of all such exchanges from all enthalpy intervals, meaning that when we break the balanced hot and cold composite curves into a number of enthalpy intervals, the area from vertical heat transfer in enthalpy interval I is given as A I 1 by H delta T Lm I, then summation of j equal to 1 to m q j for I. This means that as heat transfer coefficient of the hot as well as cold streams in I enthalpy interval is considered to be fixed or constant, the H comes out, and in a enthalpy interval I, if the log mean temperature difference is delta T L M I, then it is also fixed for that interval. So, H and delta T L M comes out, and what is changing is Q j, and Q j is the amount of heat received or given by a cold stream or hot stream in the interval I, and in this interval there can be m number of streams, which includes cold streams and hot streams and the utilities. Therefore, the minimum total area could be taken as the sum of areas of all such heat exchangers from all such enthalpy intervals, and we can find out the total area A is equal to summation of areas of intervals, enthalpy intervals I is equal to 1 to n. That means, there are n number of enthalpy intervals considered in balanced hot and cold composite curves. So, our equation is given by this. Where delta T L M I is the logarithmic mean temperature difference for the ith interval, Q j is the enthalpy change of the jth stream in ith interval, which considers both cold as well as hot streams and utility streams. H is the heat transfer coefficient, which is equal for all streams in this case. N stands for the number of enthalpy intervals and m is the number of streams in a enthalpy interval, and the value of m will change with I, and this is so because at different temperature intervals there will be different number of hot and cold streams. The summation over the streams existing in each enthalpy interval may be splitted into two summations. The Q j here represents cold streams, hot streams and utility streams, cold utility and hot utility. This summation can be splitted into two summations, one for the hot streams and other for the cold streams. When I say hot streams, it includes the utilities, and when I say cold stream, it includes the cold utility. Within an enthalpy interval, all the hot streams undergo the same temperature difference. That means, in a I interval, enthalpy interval, all the hot streams present in the BHCC will rise to the same temperature difference, which is dTH. Similarly, all cold streams will be heated up by dCTC, and if we assume Q is equal to mCp dt, then the Q for hot stream will be mCp dHTH, and for cold it will be mCp dTC. If I do so, then Q can be substituted by mCp dt, and if we do this, this equation converts into this equation. What more has been done, that Q has been divided by H, where H is a constant value in this case. So, this can be written as delta T H 1 by H summation C P H, where this C P is the specific mass flow rate multiplication for hot streams, and here this is for cold streams. So, this equation converts into this equation. In addition to providing necessary information to predict targets, the composite curves also contain the necessary information to predict network heat transfer area. To calculate the network area from composite curve, utility stream must be included with the process streams in the composite curves to obtain balanced composite curves. Because in area targeting, the area of heaters as well as coolers are also included, and this only we can find out if we take a balanced composite curve. The balanced composite curves are divided into vertical enthalpy intervals as discussed. Now, let us take an example. So, for this we take this example of 2 hot streams, 2 cold streams, 1 hot utility and 1 cold utility. The supply and target temperatures of hot streams are given. Supply temperature of H 1 is 175 and target temperature is 45, MCP, that is capital Cp is 10 and heat transfer coefficient is 2. Now, when we are going for area targeting, this column is added extra. That means, heat transfer coefficient of all the streams must be available with the stream data table if we are performing area targeting. Now, C 1, this is cold stream 1, the supply temperature is 20, targeted temperature is 155 and the capital Cp value which is 20 here and the heat transfer coefficient is 0.2. Here we will observe that the heat transfer coefficient of all the streams are equal, and the algorithm which we are using is for heat transfer coefficient of all streams equal, and that is why we find this. The H 2 is supply temperature 125, the target temperature 65 and the capital Cp value is 40, like this. The steam is at 100 degree centigrade and the target temperature is 179 degree centigrade, 1 degree less than this. I have already explained why we take this, because the Cp value of a steam condensing is infinite. To safeguard this, we see that the value of steam is changing by a degree or so, and in practical situation also it will change to some extent. So, that the Cp value becomes non-infinite value. The cold water inlet temperature is 15, supply temperature, and it rises to 25 degree centigrade, and the steam side heat transfer coefficients are constant at 0.2 and the delta T minimum taken is 20 degree centigrade. Now, our job is to find out the balanced composite curve. The procedure for plotting balanced hot composite curve and cold composite curve is the same as hot composite curve and cold composite curve, except that the utilities are also considered as additional streams. Step 1, calculation of minimum hot and cold utilities. Once the stream table data is available to us, we can go for a PTA and then we can find out what is the minimum hot utility requirement. This is in this case 605 kilowatt and minimum cold utility requirement is 525 kilowatt. Now, the next step is that once the values of utilities or the amount of utilities are known, we will try to calculate the capital Cp or MCP value of hot utility as well as MCP value of cold utility. So, here MCP value of hot utility is 605 divided by 180 minus 179. So, it comes out to be 605 kilowatt per degree centigrade. Similarly, the capital Cp or MCP value of the cold utility is 52.5 kilowatt per degree centigrade. Now, what we do to find out the required data to plot a balanced hot composite curve, we will only consider the hot streams and hot utility streams for this purpose from the stream data, and we will put the temperature levels in rising order. So, 45, then comes 65, and then comes 125, 175, 179, 180. So, there are increasing order. We have put this data in increasing order. So, these are the temperature level data, and these are the intervals, temperature intervals. Now, we can plot the streams. So, H1 stream moves from 175 to 45. The it has got a Cp value of 10. H2 stream is 125 to this, is from this to this, this is from this to this, and steam is from 180 to 179. Now, we will compute the MCP values for hot streams at different temperature intervals. This is 10 because in this temperature interval 65 to 45, there is only one hot stream present and its MCP value is 10. But in this temperature interval 125 to 65, two hot streams are available, whose combined MCP value is 10 plus 40 is equal to 50, and so on so forth. We can fill up this column. Now, we can calculate QHP, that means, what is the heat available in this temperature intervals, because we are integrating based on temperature intervals. So, heat available is the delta T of this into the MCP values. So, here this is 10 and the delta T value is 65 minus 45, 20. So, 20 into 10 is 200, and we can fill it up like this. Now, cumulative heat available in these intervals is necessary to plot the balanced hot composite curve. So, we find out cumulative. In this the value is 200. For this temperature level it is 3000 for plus 200, that is 3200. So, this is 3200, and for this it will be this value plus this value plus this value, and so on so forth. Now, based on that cumulative value and the temperature levels, we can plot the balanced hot composite curve. Now, our balanced hot composite curve is ready. So, the next step is to find out data for plotting the balanced cold composite curve. So, for the balanced cold composite curve, in the similar manner we have computed the MCP of cold composite curve, then QCB, then cumulative QCB. Once this data is known to us, we can plot the balanced cold composite curve. Then we have to put these two curves in one plot, so that the delta T minimum is 20 degree centigrade. Now, this point we will see that in the balanced hot composite curve or the balanced cold composite curve, where the line is changing slope, that point is known, because this is the point where either the inlet temperature or the outlet temperature of the stream, individual stream exists. So, that is why these temperatures are known where the slope is changing. So, this temperature is known, but this corresponding this temperature is not known for the cold. Now, cold slope changes at this point. So, this temperature is known, but the corresponding temperature at the hot composite curve is not known. Similarly, we can plot this. Now, what we will do, our next job is to find out the temperatures of the hot composite, balanced hot composite curve and balanced cold composite curve where it is not known. For that, we will put up our cumulative hot, cumulative cold enthalpies, and we will merge them by omitting cumulative enthalpies common to both values, and the entries are then stored in ascending order. This identifies all the points where composite curve has a vertex. And after that it is 262.5, then 625, then 925. So, these are in ascending order. Now, our aim is to find out the interval temperatures where it is not available. Now, 45 is available, this is hot inlet temperature. So, at 200, which is a cumulative value taken from hot balanced hot composite curve, the temperature is 65, then it is 3200. So, 3200 is this, here I have a temperature. Similarly, other temperatures are written. So, for hot composite curve, this temperature, this temperature, this temperature and this temperature is not known. Similarly, I can have for 0 this is 15, we have written the 15, then next comes 262.5, 262.5 we have a temperature for balanced cold composite curve, it goes there. Similarly, here. So, the corresponding temperatures of the cold composite curve corresponding to 125 is not known, corresponding to 175 is not known, 179 is not known. Similarly, corresponding to 65, this temperature is not known, for corresponding to 20, this temperature is not known, this temperature is not known, this temperature is not known. So, main job is now to find out this temperature, the missing temperatures. Why we are doing so? Because for a enthalpy interval, all the 4 temperatures, that is 2 hot temperatures and 2 cold temperatures should be known, and if it is not known, we cannot find out the delta T Lm, that is log mean temperature difference, and hence all the temperatures, missing temperatures should be first found out. So, these are the equations through which we do, this is basically a linear interpolation equations, and we have discussed this in area targeting. So, I am quickly skip this. So, we are computing the unknown temperatures, that shows a example how to compute the temperature. So, this unknown temperature was computed using this equation. Similarly, we will fill it up. Tci is equal to this known temperature minus this enthalpy values, and then we also use the summation of Cp values from this area, and we find out this is 18.81. So, now we are able to fill up all the temperatures required for the computation of LMTD. Now, our job is to find out the MCP by H values for the hot as well as cold. That is very simple. MCP by H will be, for this the MCP is 0, for this temperature interval the MCP is 10 and our H value is 0.2. So, it is 10 divided by 0.2 is 50. So, 50 comes here. Similarly, for this the MCP value is 10 plus 40, then divided by 0.2. So, it becomes 250. In the similar manner, we can also find out the MCP by H values for cold, which are given in this column. Why we are doing this? Basically, our aim is to compute the Q value, and Q is MCP dt. So, it is Q by H it will compute, because we have computed MCP by H. So, Q by H will be MCP by H into delta T. So, Q by H is equal to, this is delta T, this is the MCP value, this is for hot, and this is the delta T value for the cold and MCP value of the cold. So, this QH is the summation of QH hot and QH cold, and QH hot is given by this delta T into 50, and this delta T which we observe here is delta T H, and this is delta T C. That means, drop in the temperature of the composite hot stream of a certain interval, that is interval 1, and rise in the temperature of the cold stream in the temperature interval 1. So, we can calculate this value and we can put it here, 2000. Similarly, for the second interval, this is the value. So, you are using these two and these two values and these two MCP by H values. So, this minus this into 250 this value, then this minus this into 262.5 this value, and we take summation of it, comes about 625. So, it goes to 625. So, we fill it up. Now, the next job is to find out LMTD. Now, LMTD. To find out the LMTD of a particular interval, 4 temperatures should be known, 2 hot temperatures and 2 cold temperatures. For the interval 1, these are 2 hot temperatures and these are the 2 cold temperatures. So, we can find out the LMTD for all the intervals, because all the temperatures are known. So, this is the equation for LMTD. For interval LMTD 1, this is 160, this is 65 minus 18.81 minus 45 minus 15 divided by log this, it becomes 37.51. So, 37.51 goes here. Similarly, we can compute LMTDs for this. So, now we have Q values, we have LMTD values, and hence we can find out the area, because Q is known, H is known, LMTD is known. So, area can be found out. So, area of each interval will be computed now. So, the first interval area is 2000 divided by 37.51, this is 2000 is Q by H and this is LMTD. So, when we divide this value with this value, we get the area of the interval. So, it is 53.31, it goes there. Similarly, we can find out the area of all the enthalpy intervals, all the 9 enthalpy intervals. So, we fill it up. Here we get 0 area, because this corresponds to a artificial point where temperature rises immediately and the enthalpy content of that link is 0. So, the total area is 1312.57 meter square. This area is the minimum area of the heat exchanger network, and we have used the Bath algorithm for this purpose. Now, we need to have a discussion on this. Energy targets can be accurately predicted by a heat cascade procedure once the value of delta T minimum is known. However, the prediction of area using area target on the other hand is not as reliable. The algorithm based on the Bath formula, Townsend and Linoff in 1984, which is most widely used, assumed vertical heat transfer between the composite curves, and the prediction of a minimum value of area is valid only if all film heat transfer coefficients for the streams are equal. This has been shown by the Linoff and Ahmed. Now, if the heat transfer coefficients are different or different in comparison to each other by 10% or so, the area which we will be computing will not be a minimum area. For cases where film heat transfer coefficients are significantly different, it will not give minimum area using the Bath algorithm in area targeting. Then the mathematical programming route, which considers non-vertical heat transfer, may be required to achieve a minimum area of the network. So, this should be kept in mind, that for the cases where film heat transfer coefficients are significantly different, that is more than 10% different, then the area which will be predicted by this algorithm, Bath algorithm, will not be minimum in nature. Then we have to use mathematical programming, but in the mathematical programming it considers non-vertical heat transfer. Thank you.